All right, today we're going to pull back the curtain on one of the most fundamental, most important processes in all of artificial intelligence. We're talking about inference. We're going to decode the actual blueprint for how AI makes decisions and comes up with its answers. So let's dive right in.
But first, let me ask you a really simple question. How do you know the grass is wet without ever seeing it rain? I mean, you might notice the dark clouds, maybe the sprinkler system just turned off, or you see the morning dew. You're using clues, right? You're figuring something out. Just hold that thought, because you're actually already an expert at this.
And that's the perfect lead-in to our first section, the art of inferring. Because to really understand how machines do this stuff, we first have to look at how we make sense of the world. It's a skill we use all the time, usually without even thinking about it. Simply put, inference is just reaching a conclusion based on evidence and reasoning. It's not some wild guess. It's all about connecting the dots using what you already know. You see the wet grass, that's your evidence. You remember that rain or sprinklers make grass wet, that's your reasoning. So you infer the most likely cause. Yeah, you can basically boil it all down to this simple formula. You take evidence, those clues from the world around you, add in your own reasoning and background knowledge, and boom, you get an inference. A brand new understanding is formed. So what happens when we try to teach a machine to do that exact same thing? This is where it gets really interesting as we move from our own human intuition into the world of machine logic.
And the parallel here is pretty striking. For us humans, it's evidence plus reasoning. For machines, well, it's data plus algorithms. The goal is exactly the same, to reach a new conclusion, but the tools are totally different. And AI isn't looking at clouds. It's crunching massive data sets using incredibly complex mathematical rules.
So here it is, the actual technical blueprint. AI inference really happens in two main stages. First, you've got the pre-filling stage. That's where the AI just gobbles up your initial prompt and processes it all at once. Then comes the decoding stage, where it generates the answer, piece by piece, or token by token. And to speed things up, it uses this clever little short-term memory system called a KV cache to keep track of what's already been said. Okay, that sounds pretty straightforward, right? Well, here's the catch. Making a machine think like this is unbelievably expensive and incredibly difficult. And this brings us right to the central challenge here, the high cost of AI inference. Let's make this real. To run just one large language model, something like Llama 2, you need 140 gigabytes of specialized video RAM. Now, to put that in perspective for you, that is way more than even the most high-end gaming PCs have. It requires multiple extremely expensive server-grade GPUs. The sheer size of these models is a massive bottleneck. And that one big problem, the massive size, it just creates this domino effect. It leads to higher computational costs, which leads to more memory usage, which leads to slower response times. That's what we call latency, and of course, huge power consumption. It's a whole cascade of problems that makes deploying these powerful AIs a gigantic engineering challenge. So if you trace it all back, this inefficiency really boils down to three root causes. First, the massive model size we just talked about. Second, there's a complex process called the attention operation, and it gets exponentially slower the longer your input text is. And third, it's that slow, one word at a time decoding approach we saw a minute ago. But hey, for every problem like this, you've got brilliant engineers working on a solution. And this brings us to the absolutely fascinating world of engineering AI for efficiency. And they're not just throwing things at the wall to see what sticks. No, they've created a systematic roadmap to tackle this problem head-on. They approach it on three distinct levels: the data level, the model level, and the system level. So first, up at the data level, you can do things like make your prompt shorter or structure the output so it can be generated more efficiently. Then, at the model level, you can actually redesign the AI's architecture to be more streamlined. And finally, down at the system level, you optimize the software and hardware that the model actually runs on. It's a full-stack attack on the problem. And for a really concrete example of this, just look at these two popular system-level tools. On one hand, you have VLLM, which uses this really clever memory management trick called paged attention to get incredible speed and efficiency. But on the other hand, you have TGI from Hugging Face, which is built for being super easy to use and reliable. Engineers have to make these kinds of choices all the time, balancing all these different trade-offs. So who are the people making these critical decisions, building these incredibly complex systems? Well, they're called AI engineers. You see, an AI engineer isn't necessarily a researcher who's inventing new theories from scratch. They're the professionals who take what already exists, these amazingly powerful pre-trained models, and they masterfully apply them to solve real-world problems, making products better and businesses way smarter.
And their job is, well, it's incredibly diverse. They design and develop models, sure, but the crucial part is they also deploy them into the real world. They are obsessed with making systems that are scalable and efficient, using practices like MLOps, you can think of that as DevOps for machine learning, and cloud tech to make sure everything just works 24/7.
And their work is absolutely all around you. From the spam detectors cleaning up your Instagram feed and the classifiers trying to fight fake news, to the systems that automatically read your resume or find you the absolute best price for a flight online. AI engineers build the intelligent systems we interact with every single day.
Okay, so we've looked at the concept, we've seen the problem, we've gone over the solutions, and we've met the people building them. But let's just zoom out for a second. Why does making AI inference efficient actually matter so much?
It really comes down to this number. AI is projected to add nearly $16 trillion to the global economy by 2030. But that economic revolution just can't happen if the technology is too slow, too expensive, and too hard for most people to actually use.
That's why this is so critical. Efficient inference is the key. It's the bridge that takes this powerful technology out of the research lab and puts it into the hands of everyone, everywhere. Efficiency is what makes AI truly, genuinely accessible.
Which leaves us with one final and, I think, really exciting question. We've decoded the blueprint. We understand the challenges, and we see the path to the solutions. So now, what will we build with an AI that is finally fast, cheap, and accessible enough for anyone to use? The possibilities, well, they're just getting started.